All right, so this is the day 3 lesson video for AP Calculus BC. And in this video, we're going to talk about two sections from your book. Section 1.3, which is going to be all about limits involving infinity. And also, I'm going to talk a little bit about the idea of continuity, which is section 1.5 in your book. Everything that I talk about in here is going to be almost purely conceptual. There's not going to be a lot of mathematical calculation that we're going to do to solve these limits. And that's really one of the main ideas. When we solve limits, for the most part, limits are things that we don't do tons and tons of calculation to solve. Maybe we do a little bit of algebraic manipulation, but more than anything else, it's understanding the behavior of the function. So let's start by talking about horizontal asymptotes. And I mentioned this in one of the previous videos, the idea that a horizontal asymptote is actually a limit. And when you learned horizontal asymptotes in Algebra 2 and in pre-cal, a lot of the way that you're taught that is, kind of shortcut rules that you use to find the horizontal asymptotes. Well, those shortcut rules are shortcuts for finding the limit at infinity or finding the limit as x approaches negative infinity. So that's what this first statement is saying here. It's the idea that as x gets infinitely large, if I'm looking at the behavior of my function and my function is approaching some constant value as x gets infinitely large, then that means I've got a horizontal asymptote in my graph. Same idea as x is going in the negative direction. As it gets larger in magnitude in the negative direction, then when I look at that graphically, if I'm approaching one specific value, it's a horizontal asymptote. And that's what you see here is we're approaching one specific value. So some unknown limit value L. Okay, so let's take a look at actually solving through some of these limits. And these are limits that you probably know the answer to when just by looking at them, but you may be solving them by using horizontal asymptote rules. And what I want you to do is start thinking about these from the standpoint of the magnitude of the function. So what I mean by that is if you look at this first example, we have the limit as x approaches infinity of x squared minus 1 over x squared plus 1. Well, I can see the answer is 1. And if you think about your horizontal asymptote rules, the degrees are equal in the numerator and the denominator. So we divide the leading coefficients. So obviously we're going to get 1. But what's really going on here is we're thinking about the magnitude of the numerator and the denominator as x gets very, very large. So as x gets very large, let's say we plugged in x is equal to 1,000. If we plugged in x is 1,000, 1,000 squared minus 1, you can see that that minus 1, when x gets really big, it starts to become insignificant. Same thing as x gets very large in the denominator. This plus 1 starts to be insignificant. And in the end, when we're looking at this function, we're really thinking of it as x squared divided by x squared for very, very large values of x, which then obviously x squared divided by x squared is 1. And that's really what's going on with that whole idea of if the degrees are equal, you can just divide the leading coefficients. So that's what I want you to be thinking about is a conceptual understanding of how these things are solved out. Okay, so here's another example of a couple of limits as x goes to infinity or negative infinity. When you see these types of limits, what should really be popping in your head is, oh, this limit is basically saying what's the horizontal asymptote as x gets very, very large, or as x gets very large in the negative direction, what are my horizontal asymptotes? Well, for inverse tangent of x, you really have to have a pretty good feel for how this function behaves graphically. And this is a graph that you should just know, inverse tangent of x. If you don't know it right now, that's fine. This is one of those prerequisite skills that you really do need to know. If you need to graph it on your calculator, you can do that. I'm going to sketch it here just as a quick reminder. So inverse tangent of x is going to look something kind of like this. Kind of looks like one of the branches of tangent, but rotated. And these horizontal asymptotes that I have are at pi over 2. And then over here, I have one at y is equal to negative pi over 2. So notice with my graphs, when I do these sketches, I'm not putting in every single detail. I'm just putting in the important parts that matter for the problem that I'm solving. So when you're using a graph as a justification for solving your limits, don't spend tons and tons of time labeling points and putting in a bunch of extra information. Just put in the bare minimum so that the person that's looking at your work can understand what your reasoning is. Okay, so now it's pretty clear. As x is growing in magnitude in the negative direction, I'm approaching a value of negative pi over 2. Same thing as x approaches infinity. When I'm going in the positive direction, you can see that we're approaching pi over 2. Okay, so again, graphically, we want to understand what's happening. Okay, so now let's take a look at this graph. It says identify likely asymptotes and express them as limits. So what I want you to do is pause the video, look at this graph, and try to identify where do you have horizontal and vertical asymptotes. So take a second, pause it, and then when you unpause it, I'll talk about that a little bit. Okay, so what you should have found is it's pretty clear. It looks like there is a vertical asymptote where x is -1. It also looks like there's a vertical asymptote where x is 2. And then potentially we have 2 horizontal asymptotes, one at y is equal to 2 and another one at y is equal to 4. Now it says express them as limits. So this is something that's going to be a little bit new. So what I want to do is I want to explain my vertical asymptotes or justify my vertical asymptotes by using limits. So for example, the limit as x approaches -1. Okay, so we know there's a vertical asymptote there. So the limit of that function as x approaches -1 would be infinity. And remember, we talked about the notation for that last time. Equal infinity doesn't mean we're actually equal to infinity. We're just describing the behavior of the function. The function is approaching an infinitely large value. Each of the one-sided limits is getting infinitely large as x approaches -1. All right, so now for this other vertical asymptote at x is equal to 2. Well, we can describe that with one-sided limits because we don't have the same behavior on both sides of this asymptote. As x approaches 2 from the left for this function, you can see that from the left, our function is approaching -infinity. As we approach 2 from the right, this function looks like it's approaching +infinity. Now, if I said, what's the limit as x approaches 2? Well, it doesn't really exist. And really, it doesn't exist either way because I've got infinity as my result, infinity and -infinity. But since the left-hand limit isn't equal to the right-hand limit, I definitely want to write this limit does not exist because I can't describe what the limit would be as x approaches 2 overall. Okay, so those are our vertical asymptotes. Let's take a look at the horizontal asymptotes. So for the horizontal asymptotes, we mentioned that looks like there's one at y is equal to 2. And that's as x moves in the negative direction. So as x is approaching -infinity, it looks like this function is approaching 2. So that is representing a horizontal asymptote for this graph at y is equal to 2. Same thing for the other horizontal asymptote that we can see when x gets very large. It looks like we're probably approaching a value of 4. Okay, so you want to get used to seeing these limits and understanding that the limits are a way of expressing that we have a vertical asymptote. So we don't have to write there's a vertical asymptote. We can write these limits, and that should trigger your brain to say, oh, okay, this means that there's a vertical asymptote or there's a horizontal asymptote based on the results that I'm seeing here. All right, so I mentioned that for the most part, we're going to solve these infinite limits conceptually. We're going to be just kind of thinking about plugging a large number in. For instance, on this one, we can see that the limit as x approaches infinity for 3x squared minus x minus 2 over 5x squared plus 4x plus 1 is equal to 3/5. But we can also solve them algebraically. And what we can do with this as our other method is we can think about, okay, what's the highest degree term here? It's x squared. So I can divide everything in both the numerator and the denominator by x squared. And I've shown you this before, but I just want to do this as a quick review because this is really the focus of this section. So I'm dividing all of these terms by x squared. And what that's going to allow me to do is it's going to allow me to solve a bunch of small, simple limits and then combine all those results together using my limit properties to get the overall result. So for this first one, you can see the x squareds cancel. That's going to approach 3. You can see that for the second one, I've got x over x squared, or basically 1 over x. When x gets large, that's going to approach 0. So here I got 3, here I got 0. 2 over x squared is obviously going to approach 0 as x gets very large. 5x squared over x squared is going to approach 5. 4x over x squared is going to approach 0. This one's also going to approach 0. And now we just combine the results. 3 minus 0 is 3. And 5 plus 0 is going to give me 5. Okay, we don't usually work them out that way because it's not necessary. But if you did need to algebraically solve out an infinite limit or a limit where x approaches infinity or negative infinity, that would be the method you would use. All right, so let's take a look at some more limits. There's 4 limits here. And what I want you to do is solve these in any way that you can. And the reality is you can solve these just by looking at them. But if you need to graph them, or if you want to try to plug numbers in or do something like that, you can do whatever you want. But I want you to pause the video, try to solve all 4 of them. And then once you're done, unpause it, and I'll go through the way that I would really prefer that you solve these. Okay, so for this first one, we've got the square root of 2x squared plus 1 divided by 3x minus 5. We're taking the limit as x approaches infinity. So again, I want you to be thinking about as x gets very, very large, it's sort of, you think about what matters when x gets really big. Well, when x gets really big, this minus 5 becomes insignificant. This plus 1 starts to become insignificant. So now I'm thinking about, okay, I essentially have square root of 2x squared over 3x, or I have x root 2 over 3x. And if you think about it that way, x root 2 over 3x, well, I'm going to plug in a positive number. So both of those expressions are going to be positive. That's just going to give me in the numerator the square root of 2 divided by 3. You could also think about that with your horizontal asymptotes, just your horizontal asymptote rules. Just divide the leading coefficients. Now, where you have to be careful with that reasoning is the next one, which is the exact same function. However, this time we're taking the limit as x approaches negative infinity. So when x approaches negative infinity, it's still the same idea. These things don't really matter as x gets very, very large. But now you want to be careful because we're using a negative number. So if I were to plug in, and I like to use 1,000 when I'm dealing with infinity just to make it easy to think about. If I were to plug in negative 1,000, well, in the numerator, I'm going to square that. It's going to become positive. And then I'm going to take the square root and I'm going to get positive 1,000. But in the denominator, I'm going to plug negative 1,000 in, and that's still going to be a negative number. So the numerator is always going to be positive. The denominator, as we go to the left on our graph, is always going to be negative. So this is going to approach negative root 2 over 3. Over 3. Okay, so fairly simple idea. But like I said, I really don't want you to be working through a bunch of stuff and graphing these all the time. I want you to be able to just look at it and do all of that in your head and just come up with a solution. So I'm really not expecting you to show work on these types of problems. I'm expecting you to do it in your head. So same idea with the next one. Take a look at, as x gets very large, which terms are the ones that, sort of matter. Well, this term is going to dominate the value of the expression, the x squared here. In the other expression, the minus x is going to grow in value and the 3 is constant. So the 3 is not going to matter when x gets very large. So essentially, I'm looking at what's going to happen when I plug in a really large number like 1,000. I'd have 1,000 squared over negative 1,000. You can see that as x gets bigger and bigger and bigger, I'm going to approach an infinitely large number in magnitude, but it's going to be negative because the denominator is always going to be negative. Okay, so now let's take a look at, let's see, we've got 3 minus x over x squared plus x. So we've sort of reversed that other function. We flipped it so that now the 3 minus x is in the numerator and the x squared plus x is in the denominator. As x gets very large, this is going to dominate. The minus x is going to dominate the value of the expression. In the denominator, the x squared is going to dominate the value of the expression. So I've essentially got negative x over x squared, or negative 1 over x. As x gets very large, that's going to approach a value of 0. Okay, so again, normally when I look at limits like this, I just look at it, write the answer down. I'm just telling you what's going on in my head to solve these out. So I'm not expecting you to show that or explain that. I'm expecting you to just look at it and get the solution. Okay, so here are your horizontal asymptote rules from Algebra 2. In some of the limits that we just solved, you can see where these rules now come from. When the degrees were equal, we divided the leading coefficients. So this first one, when the degree of the numerator was bigger than the degree of the denominator, then we don't have a horizontal asymptote. That means our function's getting very, very large in magnitude, either in the positive or the negative direction. And then the last one, when the numerator has a degree smaller than the denominator, that was the one where you're going to approach y is equal to 0. So that's where those rules all come from, shortcut for the types of limits that we just solved. Now, where you've got to be careful with this, when you're looking at magnitudes like this, it can be a little bit tricky. We've got here the square root of x squared plus 1 minus x. This limit approaches a value of 0. And it has to do with the whole idea that in the end, we're sort of looking at x minus x, because when I look at the degree of x squared and I square root it, that's like a degree 1. For the second one, I've got x squared minus x this time. The difference now is the x squared is growing in magnitude much faster than the x. So, when x is 500, when x is 1,000, when x is 2,000, and so on, this first term is going to dominate the value of the expression. And so I'm not subtracting away as much value as the x squared. So I'm going to keep growing and growing in value, and it's going to approach infinity. Don't forget, we do have this direct substitution property. That's kind of what I'm doing as a way of reasoning through these. So remember, with the direct substitution property, you just plug a number in. So that's what I'm thinking about when I plug in like 1,000. I know that my limits are approaching infinity, but I'm really sort of doing like a version of direct substitution. Direct substitution was you just plug a number in. Like for this first one, you get 0 over 2. This just gives me 0. For the second one, I get 5 minus 6. That gives me negative 1. So that's what I'm doing with those infinite limits when I plug in like 1,000 or negative 1,000. And then I'm thinking about, okay, if I plug in a number larger than 1,000 or smaller than negative 1,000, is that trend, what's the trend going to be? Okay, so let's move on to continuity. And this is another thing where it's like I mentioned at the beginning, this is really kind of entirely conceptual. So with continuity, there is a definition for continuity. And this is one of those things that is super, super important in this class. In order for me to justify that a function is continuous, most people can look at a function and they can tell if it's continuous. It's one of the kind of basic ways of thinking about it is, okay, can I draw this function without picking up my pencil? That's what a lot of people learn as if the function's continuous. But mathematically, the way that I justify it is I'm looking at the limit value and the function value. If the limit value is equal to the function value, then I know the function is continuous at that point. Most of the time with a graph, you can just look at it and you can know that it's continuous. But we do have, kind of special cases that show up. So these 3 graphs that are side by side here, we're looking at 3 different scenarios. And what we're trying to do is figure out, are we continuous at the point C? Well, at the point C, it's pretty obvious that none of these are continuous. So this one's got a hole in the graph. Here we've got a jump discontinuity. And here we've got this point that's defined outside of where the limit is. So for different reasons, these are all not continuous. The first one, we don't have a function value defined. So there's no way for me to satisfy this statement. I can't say the limit value equals the function value because there is no function value. For the second one, the limit value doesn't exist. So again, that statement can't be true. And for the third one, we do have a limit value and we do have a function value, but they're not the same. So if I want to justify whether a function is continuous, I'm always thinking about, continuity at a point being, does the limit value equal the function value at that point? All right, so I want you to take a minute and you can write it down. What I want you to do is pause the video and I want you to write down all of the intervals where this function is continuous. This is a little bit tricky, but I want you to do the best you can with it. Think about the limit value being equal to the function value. So pause the video, write down your intervals, and then we'll talk about that. Okay, so in terms of intervals where this function is continuous, clearly between 0 and 1, my function is continuous. Between 1 and 2, it's continuous. And between 2 and 4, it's continuous. Where I mentioned that this was a little tricky, where this is a little bit trickier at these endpoints. So at these endpoints, for example, at 0, notice that we have a function value defined at 0. So ask yourself, would the limit exist at 0? Remember the definition of a limit. Does the left-hand limit equal the right-hand limit at 0? And the answer would be no, the limit doesn't exist at 0 because there is no left-hand limit at 0. However, there is a special rule for continuity when we're dealing with endpoints. When we're dealing with endpoints, we only have to look at the one-sided limit. So if the one-sided limit is equal to the function value, then the function is continuous. So for my first interval, I'm going to write this in interval notation. Between 0 and 1, I know this function is continuous. Pretty clearly, when I'm at 1, the function, let me rewrite that. The function is not continuous at 1 because we've got that jump discontinuity there. Clearly, the limit value and the function value are different at 1. In fact, the limit value doesn't exist at 1. Okay, so now between 1 and 2, we've also got another interval here between 1 and 2. We already said the function's not continuous at 1, and we can see at 2, it's clearly not continuous. And then the last interval, we know we're going to go from 2 all the way out to 4. And we're in a similar situation. We're at an endpoint. So at the endpoint, we just look at the one-sided limit being equal to the function value there. So I gave you that in advance of the rule just because I wanted you to kind of think about, it's kind of weird when you're at endpoints. And so we actually have a special rule when we're at endpoints. So the first thing is, if I say a function is continuous on an open interval, that means that the limit value is equal to the function value at every point within that interval. And this is what we looked at in particular on that last problem. When we're at an endpoint, notice we're only looking at the one-sided limit. Same thing when we're at the right endpoint. We're only looking at the one-sided limit being equal to the function value. So a little bit different from a continuity standpoint. Continuity is one of those things that is super, super easy, but there's a lot of subtle details in there that you have to know to have a true understanding of continuity. Okay, so this is where we're going to get into something that I like to call verbal gymnastics a little bit with continuity. So a continuous function is one that is continuous at every point of its domain. So what that means is, if I say a function is continuous, that means if you see any discontinuities in that graph, I am eliminating those discontinuities by restricting them from the domain. So let me show you an example of what I mean by that. So it says y equals 1 over x is considered to be a continuous function. Why is that the case? Well, if I said y equals 1 over x is continuous, it's obvious from this graph that you can see over here on the right, it's obvious from the graph that the function is not continuous at x is equal to 0. But by stating that the function is continuous, I am restricting the domain. I'm saying x cannot be equal to 0. I have now eliminated x equals 0 from my domain. So it's all in the wording when it comes to continuity. And that's why I said it's sort of verbal gymnastics, because you've got to be very, very careful. The way you word things can impact what what the justification is, what the result is. So another example here, it says f of x equals x squared minus 1 over x minus 1 is continuous. So again, you can see on this graph, there's a hole in this graph, right? There's a hole at x is equal to 1. If I just didn't say anything and said, is this function continuous? Well, if I said, is it continuous? Most people would probably say, no, that's not continuous. But this statement is saying this is continuous. By saying it's continuous, I am implying that x cannot be equal to 1. So if you get an open-ended question like that that says, is the function continuous? You can answer it either way as long as you justify it correctly. I could say the f of x is not continuous because there's no function value at 1. Or I can say f of x is continuous because x equals 1 is not in the domain of the function. And it's all in how you answer the question. Both answers would be correct. So be really careful with that. Okay, so here is something that we talked about previously in one of the earlier lessons. Here's the same function where now we've filled in a hole in the graph. So you'll see this on your assignment. It'll say, rewrite this function so that it is continuous everywhere. Well, this function, and in this graph, obviously we had an issue at the point where x was equal to 1. So what we do to figure out what that point needs to be is we take the limit at x is equal to 1, and then we figure out, okay, what is the function approaching at x is 1? And then we can just define a piecewise function and fill in that hole in the graph. So you'll see some problems like that on the assignment where they're going to say, rewrite this so the function is continuous. That's what they're wanting you to do, is figure out what the limit is at that point, and then use the definition of continuity, make the limit value equal to the function value. All right, we've got different types of discontinuities here. We've got discontinuities that you're familiar with and maybe one that you haven't seen as much of. So we have a jump or a step discontinuity. You can graph that, but that just means that obviously we've got a point in our graph where we jump from one value to another. So the limit value doesn't exist. At this point, it would be at 0. An infinite discontinuity, another term for that is a vertical asymptote. Removable discontinuity we just looked at. That's a hole in the graph. The last one is called an oscillating discontinuity. And I want to show you this one on the calculator. So this is one where it's not quite so obvious. So we have the sine of 1 over x. If I were to graph that on the standard window, this is what it looks like. It's pretty obvious on the standard window that something weird's going on at 0. What I'm going to do is I'm going to zoom in on the origin to get a better feel for what's happening. And you can see still there's something weird going on here. It almost looks like there's a left-hand limit and a right-hand limit, but that's just because there's only so many pixels on this screen. If I zoom in even more, you start to see that the value of this function is actually going up and down faster and faster the closer I get to 0. So the value is oscillating back and forth across the x-axis. So that's where the term oscillating discontinuity comes from. There's no limit from the right side. There's no limit from the left side, because the closer I get to 0, the more that graph is just going to oscillate back and forth across the x-axis. I'm going to zoom in a little bit more, and you'll see that when I zoom in even more, all it does is just oscillate more and more and more. And if I did this enough, eventually you would just see a solid blue screen, because there's so many of those function lines going up and down and up and down and up and down so fast that they're all just starting to look like one big block of blue. So there's no limit here, because the left-hand limit and right-hand limit both don't exist. There is also no function value. So that is what we call an oscillating discontinuity. A good way to identify if you have an oscillating discontinuity, when you see these trig functions, a sine or a cosine with a 1 over x or like a 1 over x squared in it, that's going to give you an indication that something weird is going to happen, because you're going to have an undefined value at 0. And you can't take the sine or the cosine of an undefined value. So be thinking about that when you're looking at the discontinuities. You know, it should be kind of an alarm in your head when you see a potential undefined value in the argument of one of your trig functions. That's a potential oscillating discontinuity. So a little bit more about continuity. If I have two functions that are continuous and I combine them in any way, it's going to result in a continuous function. So you can see if I add, these two functions are called f and g. If I add them together, I get a continuous function. If I subtract them, if I multiply by a constant, if I multiply the two functions together, even if I divide the two functions, I still have a continuous function, provided that the denominator isn't going to be 0 at any point. Okay, so when we talk about continuous functions, a lot of functions are just considered to be continuous. So any polynomial function just is continuous everywhere. But for trig functions, we typically say trig functions are continuous. So think about the tangent graph. The tangent graph has vertical asymptotes in it, but we say it's a continuous function. So remember, if I say the tangent graph is continuous, I'm implying domain restrictions. Same thing with a log function. Like if you think of the natural log of x, we know it's not defined at 0, and we know we can't take the log of a negative. So again, by saying a log function is continuous, I'm just implying a domain restriction. So that's really what's going on with this. It's a matter of justifying based on the way that you state it. So if I say it's continuous, that is implying domain restrictions if you know there's points where the function would be discontinuous. All right, and then the last thing before we get into intermediate value theorem, when we evaluate these limits, what you can do, one of the properties that we didn't really talk a lot about before, it's called the composite property. If I have a function within my function, you can take the limit either of the outside function first or of the inside function first. So you can see this example. We're taking the limit of arc sine or inverse sine of 1 minus root x over 1 minus x. Well, I can take the limit of, right now, I don't, taking the limit as x approaches 1 of arc sine, that's something I can't really do very easily. But if I were to take the limit of 1 minus root x over 1 minus x, that's something that we can do. We'd multiply by the conjugate, and then we could go through and find that limit. And then once we know the result of that limit, we take the arc sine or the inverse sine of that limit, and that gives us the result. So keep that in mind when you have those composite functions. You have options in terms of how to go about it. There's sort of a hard way, try to do the whole function all together. And then there's an easier way where you just work with the inside function and then apply the outside function to that result. All right, last thing on here, and this is a super, super important theorem within calculus. It's called the intermediate value theorem. I typically refer to this theorem as the common sense theorem. It's one of those things where, and you'll see in this example, you know that it's true just by thinking about it. But there is a mathematical justification that you have to do to justify how you know what is obvious is true. So what we're looking at here is we're looking at this graph, and we have a function that is starting at one point, some function value, and it's ending at another function value. We know it's a continuous function. And so the question would be, if my function value goes from f of a to f of b, did I have to have a point in my domain where the function value was equal to this y naught, which is a number that's somewhere between f of a and f of b? And so like if you think about it, if you're in your car, if you accelerate from 10 miles an hour to 40 miles an hour, at some point were you going 25 miles an hour? Obviously, yes. We couldn't skip over 25 miles an hour. It's not possible because that's a continuous function as you accelerate. So that's the idea here, is we're just kind of going through and we're saying, okay, this is kind of common sense, right? But the justification for this is that we have to have a continuous function in order for that to be true. So this is what the intermediate value theorem says. A function y equals f of x that is continuous on a closed interval a to b takes on every value between f of a and f of b. Those are the two endpoint values. In other words, if we have y naught, which is between f of a and f of b, then our function has to be equal to y naught for some x value c within our interval a to b. And I'll show you an example of how you would do this. So this question says, explain why the function f of x is x cubed plus 2x minus 1 must have a 0 in the interval 0 to 1. So it's not as simple as just saying, oh, because the function's continuous. There's actually some very specific details that you have to include in your explanation. And the reason I'm going to be super picky about this is because this is actually something that is very likely to show up on your AP exam when you do your free response part of your AP exam. And your justification has to include what's within the intermediate value theorem. So what we do in a situation like this is we say, okay, what's f of 0? Well, my function was x cubed plus 2x minus 1. F of 0 is negative 1. And then I can also say, all right, what's f of 1? Well, if I plug 1 into that function, I'm going to get 1 plus 2 minus 1. That's going to give me 2. So my function went from a negative to a positive. Did I have to cross over 0 if I went from negative 1 to 2 within that interval? And the answer is obviously yes, because this is a continuous function. I went from negative to positive. I know I crossed over 0. So the way we justify it is actually to write out a statement. And I'm going to write out an example and I'll show you the key parts that have to be in. You don't have to word your statement exactly like I do, but you have to have the same key information in your statement. I usually start it like this: because f of 0 is equal to negative 1 and f of 1 is equal to 2, there must be at least one 0 in the interval. Let's see, what was our interval? 0 to 1. Because, or I'll say since I already used because, since f of x is continuous. And I'm going to say this function is actually continuous everywhere. I could say because f of x is continuous on the interval, but in this case, this function is continuous everywhere. Okay, so what I've done is basically stated what the intermediate value theorem says. But these are the key things that I'm going to look for if I ask you to write a statement like this out. And at some point down the road, you're going to have a question like this on your test. And you're going to have to actually submit a written response to me, and you're going to have to justify the intermediate value theorem. So there's a few things that need to be here. You need to have the function values that are indicating the behavior that you want. It's going from negative to positive. Also, notice that I said there's at least one 0. I know for sure I went from negative to positive between 0 and 1. I did it at least one time. The graph could go back and forth across the x-axis a bunch of times. I kind of know that it doesn't in this case because it's a cubic function. But, you know, if you don't know for sure, then you want to say there's at least that many times it's going to happen. So at least in this case, 1 0. I just noticed I left out an E. There's at least 1 0 in the interval. So I also want to state which interval I'm referencing. And then the last part is I stated that my function is continuous either everywhere or on the interval that I'm looking at. So those things that I have circled, those are the key things you need to have in your statement. Like I said, you can use different wording as long as you have the same key pieces of information, which are the key pieces of the intermediate value theorem. Okay, so that's everything for this lesson. Make sure you do the assignment associated with this, and just let me know if you have any questions.